So, if we look into an example of this stack, like the first example STMFD stack pointer, then this exclamatory mark is there, means it will be following that auto increment auto decrement mode, either of them. Then here I can specify the registers that I want to save. Okay. So, this R0, R1, R3 to R5. So, if this is the previous stack pointer, now if it is so it is empty descending stack. So, I assume that the memory address decreases when I go towards the lower direction. So, the our 0 is here, the 0 is address 0 is on this side, and this side I have got the highest address. So, the stack pointer value is decremented and the values are stored here. So, this is a full stack. So, it was pointing to the location till which it was having the value, and now the before putting the next value, the stack pointer is decremented and the value is saved here. So, that way it continues. So, the new stack pointer will be pointing to this, because the up to this much the stack is full now. So, it will be pointing to this. Now, if we are having say the STMED, then the previous stack pointer was pointing to the next empty slot. So, from that point onwards the values of the registers will be saved, and this stack pointer will be pointing to the next empty slot after doing this operation. Then STMFA, so this is it is also full ascending stack. Now, the previous stack pointer was here. So, it is ascending stack. So, stack pointer value will be incremented. So, it will be going towards the higher addresses, and then this it is full. So, this stack pointer will point to the last field entry, and this one STMEA. So, this stack pointer value will be in decremented, it is going in the ascending direction. So, this is so this is going this is the stack pointer value will be incremented, it is going in the ascending direction. This side I have got highest address, this side I have got lowest address. Now, these values will be saved in the corresponding locations. Now, you see that in all the cases, if you look into the pattern in which they are saved, now everywhere I am writing like R0, R1, R3 to R5, but they are not saved in the same order. So, you see that in this, if you look into this particular example, then this this is the lower address, and you see the R0 register has been saved at the lowest address, then the R1, then R3, R4 and R5. Similarly, here, so R0 register has gone to the lowest address and the R3, R4, R5, whereas in this case R0 register has gone to the lowest address, and this R5 the R0 it has gone to the lowest address, and R5 has gone to the highest address. So, in all the saving, so it is following that convention that the higher order register is going to higher order memory address. And it one beautiful thing about this processor ARM processor is that it does not matter in which order you specify these registers. So, even if you write like say R3, R5, R0, R1, R4. So, if you simply write like this also, then also the saving will be same as this one, because it will always follow that whatever be the lowest register, so that should go to the lowest address. Similarly, whatever is this the R0 is the lowest one, so R0 will come here, then R1 is the lowest, R1 will come here. So, whatever be the order in which you have specified it here, so it does not matter. So, it will be taking, it will be saving in that order only. Similarly, whenever you are loading the value, so if you are using this LDM instruction, so LDM ED instruction, then whatever be the order in which you specify these registers, it does not matter. The lowest order location content will be retrieved into the lowest register. That way, the highest order content will be retrieved into the highest register. So, this is very much useful. I will take an example and try to explain, like when previously in 8085 or 8051, when we discussed about one ISR structure. So, we said that if this is the body of the ISR, so before that you need to save the registers, and after the body you need to restore registers, or for that matter if it is in any other procedure also, any other subroutine also, and that you need to save registers and restore. So, we have to do it like this, and we have to be careful, like if you have written here like say push push H, then push D. Then while retrieving, so you have to first do a pop D and then a pop H. So, you have to do it in the other direction. So, you have to follow the order in which you have pushed it while popping. So, you have to pop in the other direction, otherwise the contents will be mixed up. So, if you do it by mistake, if you do here pop D, pop H and pop D, then the register values will be corrupted. So, but many times what happens is that the programmers while writing their programs, so they do this type of mistakes, and it is they may not be following the order in which the registers have been pushed, and they forget to retrieve in the reverse order. Okay. So, this is a very common mistake that has been detected for the assembly language programmers. So, what these ARM people have done, they have just got rid of this problem. How? It does not matter. So, as we have seen here, it does not matter in which order you have specified this push pop, okay, or this these registers in this saving, whatever be the order. So, it does not matter. So, it will always take R0 as the lowest register that is specified here. So, it will put it in the lowest address. So, then it will find that R3 is the next lowest register. So, it will put R1, R1 is the next lowest register. So, it will put R1 as the next lowest address. Then it will find, it will analyze all these registers and find R3. So, R3 it will be putting here, so at the next lowest address. So, this way it will do. So, it is irrespective of the order in which you have specified it in this here. So, it does not matter. So, after doing this, so if you are after this SDM FD ED, sometime later if you have written like LDM ED stack pointer, and then in the register if you have written like R5, R0, R1, R4, R3. So, then also it does not matter, it will be retrieving these values properly onto those registers. Okay. So, that is the good thing about this ARM processor. So, next we will be looking into that large block of data transfer, like that moves instruction that we have seen in case of that we know about this moves instruction in 8086 type of processors. So, here the instruction that will be useful are STMIA and LDMIA, which is increment after, then STMIB and LDMIB for decrement for increment before, then STMIA DA and LDMDA decrement after, and this is decrement before. So, this is one example that I have taken. Suppose I have got a block of data, and this block of data is pointed to by R12. So, R12 is pointing to the block of data that we have, and source data. So, this is the source, and we want to put it to this destination, which is pointed to by R14. So, R14 points to this destination, and not here, R14 points to the end of the block. So, R14 is this one, R14 is pointing to the end of the block, and R13 is the beginning of the destination. So, this is R13. So, in this case, so we have got this. So, this R0 to R11, these 12 registers are free for this data transfer operation. So, this LDMIA instruction. So, what I am doing? So, R12 exclamatory mark R0 to R11. So, it will be copying the content from these locations pointed to by R12 into the registers R0 to R11. So, each of these registers are 4 byte wide. So, total 48 bytes of data will be transferred by this instruction from memory to the R0 to R11 registers. After that, it will be using one STMIA instruction. Now, R13 was pointing to the destination. So, it will be transferring the 48 bytes of data from R0 to R11 to the memory locations pointed to by R13, and after every transfer, this value will be incremented, R13 value will be incremented because the exclamatory mark is there. Then we compare R12 with R14 to see whether we have reached the destination. If they are not equal, if the destination is not reached, then it will go back to this loop and it will do the next 48 bytes of transfer. So, this way it will go on. So, but this is a very preliminary type of routine. You can see that it does not check for any overlapping of the blocks. it does not check for any the data bytes that you are transferring, the data block may not be an integer multiple of 48. So, all those problems are there, but still, so this gives us some idea about how this large block of data can be transferred. So, next we look into the multiplication instruction. So, multiplication instruction in ARM processor, that is very powerful. We have seen that 8085 does not have any multiplication operation. In case of 8051 we have got multiplication, but it is 8-bit multiplication only, and the instruction format is fixed. So, A and B registers, they should have the 2 operands, and this MUL AB instruction, so it was just multiplying the numbers A and B, numbers in A and B. Now, in ARM processor, this multiplication has got many variants, like we have got integer multiplication. So, which is 32 bit, which will give you a 32 bit result. Then there is a long integer multiplication that gives 64 bit result, and there is a multiply accumulate instruction. So, for this multiplication and addition, so multiplication over arrays and all that. So, the instructions that we have is MUL for 32 bit multiplication, MULA for 32 bit multiply accumulate, and then this UMULL. So, it is 64 bit unsigned multiply, then UMULL. So, this second L is for long, and this U is for unsigned, and so this is the multiply accumulate. So, typical examples are like this. So, multiply MUL R0 R1 R2. So, R0 gets R1 into R2, MULA R0 R1 R2 R3. So, this is an exception. So, it is a 4 operand instruction, whereas in ARM in most of the instruction it is a 3 operand instruction. This is a 4 operand instruction, where R0 will get R1 into R2 plus R3. So, this is good, because this MULA instruction, so this can be used for doing that operations, like if I have got this y equal to sigma ai xi. So, what I can do, I can allocate this y to say R3, and then this ai to this R1 registers and xi to R2 registers, and then I can do this MULA, and then after that we move this R0 register value to R3 register. So, that way I can do this multiply accumulate, I can utilize this multiply accumulate to for doing this multiplication and addition simultaneously. So, the next instruction that we will have is this some restriction on the multiplication instruction, like destination and source, they cannot be the same register. So, this is something very interesting, because so maybe that this destination register, so the source register will get modified during the operation. So, as a result, if you are using it as destination also, then the register content will get corrupted. So, you will not get the correct value. So, this destination and source cannot be same register. Then this R15 register, the program counter, it cannot be used for multiplication purpose. Okay. The program counter cannot be used, and it uses Booth's algorithm. So, Booth's algorithm is a well known multiplication algorithm. So, you can get it into computer architecture books. So, this is a multiplication algorithm. So, that is quite efficient, and here for each pair of bits it takes 1 cycle. So, and 1 more cycle is needed to start the instruction. So, it is like this, that if I have got say one 32 bit number, if I have got say one 32 bit number, 2 32 bit numbers to be multiplied, then for each pair of bits, so it will take 1 cycle. So, it's these are the pairs of bits. So, we will have 16 such pairs, there will be 16 such pairs. So, that will take 16 cycles, plus 1 cycle will be needed for starting the instruction. So, that way this multiplication will take 17 cycles. But there is another interesting thing which is known as early termination. So, this is the early termination. So, what is it? It is like this, that whenever the content source register content becomes 0, like say if we are say multiplying, if you are multiplying 2 numbers, and if you see that the numbers are say 4 multiplied by say 5, something like that. So, 4 is in the source register. So, it is 1 0 0, and these bits are all 0. So, when I do grouping, so I do a grouping of these 2 bits, these 2 bits, then after that I find that, so after these 2 bits have been processed, so this whole thing is shifted, and I see that the register is the source register that contained 4 initially is no more is not yet 0. Okay. So, it is still having the value 1. So, next time, so this will be shifted next time. So, once this shifting is done, so 0 1 comes to the least significant 2 positions. Now, I will be so I will do that multiplication with this 0 1 of that 5, and then it will be shifted further. So, this 0 1 will go out of the register and the source register content will become 0, and when the source register content becomes 0, there is no point trying to do multiplication with 5 and generate this partial sums to be added finally. Okay. So, that way the algorithm will terminate. So, it will not continue once that source register content becomes 0, and so that leads to the condition called early terminate, and that helps in speeding up the multiplication operation. So, this is a typical example. Say suppose we want to multiply 18 by minus 1. So, if we take 18 as the source, then it will take 4 cycles, because 18 is so this is say, so this is the number 18. So, this is the first 4, the next 4. So, it is like that. So, rest of the bits are all 0, and I am trying to multiply it by minus 1. So, for minus 1 all these bits are 1, all the bits are 1. Now, if you are using 18 as the source register, then first for these 2 bits, so it will take 1 cycle, then for this one it will take 1 cycle, and for these 2 bits it will take 1 cycle. After that the source register will become 0. So, this takes 3 cycles plus 1 cycle to start the instruction. So, total 4 cycles will be needed if 18 is kept as the source. On the other hand, if you take minus 1 at the source, that is you try to do this multiplication minus 1 multiplied by 18, then for this minus 1 all the bits are 1. So, it will take total 17 cycles as we had calculated previously. For every pair it will take 1 cycle, the 16 such pairs plus 1 cycle to start the instruction, total 17 cycles will be needed for doing that multiplication operation if minus 1 is taken as the source. So, here the compiler has got a role to play. So, whenever it will find that it is multiplying by some constant, so it can try to see how many cycles will be needed if that constant is taken as the first operand, and if that number is profitable, then it will be putting that constant as the first operand, otherwise it will put the variable as the first operand, or if it is multiplying 2 constants, so it can do that way. So, it can put one of them as the first operand, whichever will require less number of cycles. Next, we will look into the software interrupt instructions. So, it forces the CPU to the supervisor mode. Now, in case of software interrupt, the instruction format is SWI #n, and it causes an exception trap to the SWI hardware vector. So, we will see what is this vector address. Okay. So, before going into this, so we need to look into this software interrupt concept a bit more. Okay. So, as I said that this software interrupts, so they are generally available as they are the software interrupts in case of say Intel family of processors. So, the corresponding instruction is INT. Okay. And the format here is INT and a number n, where this n is a 8-bit number, Okay. So, so in a program, so if you are writing a program, so somewhere you can put like so INT x, where x is an 8-bit number, and then this x will be multiplied by 8. So, this x will be multiplied by some 8, and accordingly it will be jumping to one particular address where this service routine will be there. So, that is the interrupt service routine. So, for the software like this INT instructions, so they are useful for OS services, as I said that it is normally useful for operating system services. So, in a program whenever you are willing to get service from the system, so you have to use this INTX instruction. Typically for example, suppose I have a program P, and after executing for some time it needs to read from keyboard, read from the keyboard device. Now, how will it read? So, the OS designer they will tell you that for reading for this keyboard it is available as INT say 5. Okay. So, if you put INT 5, so it will invoke that read from keyboard service, and at the end of this the keyboard the value that the user has pressed, that key value will be available in some particular register, say R5, the R5 register will have the key. So, what you can do in your program, so when you have got to read from keyboard, so you can translate it into one INT 5 instruction, and then on getting when you return from this interrupt, you know that the R5 register will have the key value. So, you can check the R5 register to see which key has been pressed by the user. So, that way you can have it. So, that whenever you need any OS services, normally the operating system designer, so they will provide you a list of such services available from the operating system, and they will be specified as this INT, and this address will be specified there. Okay. And you can use it in your program. Now, in case of ARM processor, so we have the similar thing, and these services. So, as I said that n is an 8-bit number, and this in case of processor, in case of say 8086 type of processor, then the address bus. So, address bus is 20-bit, okay, and then this 8-bit number. So, it can point to some fixed memory location. So, it is not arbitrarily distributed. So, it is multiplied by 8, and those locations will be reached. So, INT 0, it will be coming to the location 0, INT 1 will come to the location 8, INT 2 will come to the location 16. So, that way it will go. So, there are fixed memory addresses where this location. So, these are actually the vectored interrupt. So, whatever be the value, so it will be coming to that location, and it will be taking it from there. So, the maximum value that I can have with this x is 255, because this is 8-bit number. So, it is 255. So, 255 multiplied by 8. So, it can you can have up to that much address dedicated for this vector table. Now, in case of ARM processor, what has happened is that we have increased this range. Okay. So, this range is increased. So, this SWI n, this n can be any of the 24 bits. So, n is a 24 bit value. So, instead of that 8 bit value, now n is a 24 bit value. So, if it is a 24 bit value, so we can have 2 power 24 different OS services. Each of these service is called a system call. So, we have got 2 power 24 different services. So, that is good, because now I can implement large number of system calls in my operating system. But the difficulty is that for each of these 2 power 24 system calls, we have to have the corresponding memory address. If the address bus is assumed to be even say 32-bit address bus, so in that case also, so the 32-bit address has to be specified. So, total I will require so for each of these I will require 4 bytes of memory space to hold the corresponding vector address. So, 2 power 24 multiplied by 4. So, 2 power 26 memory locations, 2 power 26 bytes of memory location will be needed to just hold the vector table, just to hold the vector table. So, 2 power 26 memory locations will be needed, and this is a huge number. Okay. So, this is your 64 MB of space. So, that will be required just to hold the that memory address. So, that is not that interrupt vector address. So, that is not advisable. So, what this ARM people have done, they have done they do it like this, that they will not go to different addresses. Whatever be the value of n that you have specified here, it will not go to different address, it will go to the same address. For all these 2 power 24 different system calls, the hardware will come to the same address, and in your software you need to differentiate between those values of n, and from there you call the routine. So, the processor gets interrupt and it comes to the same address. From that point, it is the interrupt service routine, its responsibility is to analyze the value of n and accordingly decide to which which procedure should be called. So, based on the service request. So, value of n is used to differentiate between the service procedure to be called. So, processor will completely ignore the value of n, because it cannot handle such a big thing. So, that is about the software interrupts. Conditional execution. So, I have already introduced it. So, that ARM, it will allow instructions to be executed conditionally. Most significant 4 bits they are used of each instruction, they are reserved as condition code. So, we have got this say R0 equal to R1 plus R2 only if the 0 flag is set. So, the EQ add. So, EQ add this EQ part. So, this will tell that addition will be done only if the 0 flag was set. So, this way this conditional execution, it is helpful, like if we have got a number of instructions and if you have got a number of condition checks and conditional execution. So, you can use it, and that way we have seen that it can be utilized to reduce unnecessary jumping in the program. So, that this conditional execution leads to straight line type of code, which helps in the pipelined execution of programs.